All right.
Go back over
Best behavior.
I mean, mainly what like the arguments are, or what the integer arguments.
So, yeah, okay. In your main program, you're going to declare an output file stream and an input file stream, and those file handles you're going to be passing into these functions. So that part you got. One side note here. When you're asking for a file name from a user, I just want to remind you that, so let's say you've got an if stream up here, and let's just call it file in, and let's say you've got a string called file name, and presumably, you know, you've read it from the user. Sadly, these file handle things don't take C++ style strings. So the syntax to open that guy to connect it to the external file name is going to be so file name is a string object. And one of the member functions in the string class is the C underscore string, str, C underscore str. What this does is it takes the string object and turns it into a C style string object, which is secretly a pointer to an array of characters. And the open command in a C++ file handle or a C++ if stream, op stream object needs to be a C style string, aka a pointer to a character array. And a string object is not that. So if you try to just shove the string object into the open command, it's going to say, I don't know how to deal with a string. I only do C strings.
What is a string object then? Because that's what I thought we were getting at when we were writing all those fake string classes.
No, a string object is a C-style string. Let's put it that way. A C-style string is literally nothing more than an array of characters. So I can't ask a C-style string how long it is. I can't append to it. I can't add two C-style strings together. I actually can, but there's a separate library, a C-string library, that'll do that for you. But a string object is, yes, it's an array of characters, but it's also member functions and various other things. And so you can't throw that into the open function. Not that there's any a priori reason why you couldn't do that. It's a design choice by the C++ spec to say you can't throw a string object in the open command.
So you just haven't.
Right, exactly, and you could trivially write an extension of the if stream class so that its one extension would be that it could take strings in open, but by default it's not that way. Jamie, go ahead.
Would that be a friend function in the string class?
What it would be, we haven't done this much, but. Gosh, I can't even remember I can't remember what the word is, but a derived class. So you would make a derived class that inherits everything from the if stream class, and then you would add this extra member function to the derived class. So it would be really simple. You would make a derived class, call it if stream 2, and let if stream 2 inherit everything from if stream. And then in the public section, you would have an open function that takes a string, and the way that you would implement it is inside you would do that.
Gotcha. Isn't that how Open Frameworks works with like OpenGL? Like an OpenGL object that they add?
Yeah, there's that's pretty common in open frameworks to essentially take an object, take a class, and then make a derived class and just add the stuff that you want to the derived class. We don't do that much. I don't do that much. David doesn't do that much here. but it's a really common practice. It's sort of one of those things that you kind of make choices when you're teaching programming, about what you're going to talk about and what you're not going to talk about. And David and I have both kind of just decided that derived classes are maybe not super important here, but if you're taking a computer science major somewhere, then you would be using derived classes all the time and inheriting stuff. It's really one of the most powerful features of the language, building derived classes and inheritance and all that sort of stuff, but it's just not something that we emphasize here. What, Jamie?
Well, because the way that I did my calculator was dumb, and I made two entirely different stacks, but I could have just extended the first stack and changed the type that, couldn't I? Or could you not change the type that?
That's not quite, I mean, you probably could have done something like that, but that's not really what I'm getting at. But
yeah. It was just, Oh, before, a ways back, is the reason that you can't do like a string for the file in.open is that because the C string is closer to like a primitive type?
Exactly.
Okay.
Yeah. In fact, if you were to look at the prototype for open in the ifstream class, it would be a car star, which is a primitive type. And you're exactly right. And so what this does is that it makes it so that you don't have to include the string header to use files. And there's sound reasons for that, right? So you're not loading all the string machinery just to use files. You're just using primitive types. So you're going to open files like that, attach them to file handles, and all of this is going to happen in main. And then you're going to be passing those file handles into these member functions. So put bit is going to take a bit, C, and it's also going to take a file handle that you've already attached to a file at some point earlier in the program. And if you'll notice when I ran my program and I have my menu function, I'm not asking you to trap errors. So for example, if somebody tries to put a bit into a file before they've actually named the file, you don't have to worry about that. Just assume that I'm using the program correctly and that I have named the file and then that I have a good file handle and putting stuff in there is legit. Put bit. So what was your question, Josh?
Oh, well, so C there is a 0 or 1.
Yes.
That's going to be put into kind of the next bit. I mean, my main question had to do with which end we're putting the bits into in the input versus or reading off from.
Okay.
In those cases.
So that's the FIFO-ness.
Yeah.
That you want to preserve FIFO. So all that really matters is that you start at the same end when you're reading and writing. That the first bit in is the first bit out. Okay, we talked a little bit about this already. No? Yes? Yes. Okay. So you can choose to put the first bit in at position 0 and go up to position 7. And then when you're reading, make sure you start at position 0 and work up to 7. That's FIFO. Or you can go from 7 down to 0 and 7 down to 0. It just has to be consistent between putting and getting.
Okay, and then get bit there is what is B supposed to be? What are you supposed to do with B if you're not at the end of a byte? Are you putting 0 or 1 in that?
Yep.
Oh, okay.
So I go in and I do my masking and I figure out what the bit is and then accordingly set the integer B to 0 or 1. Notice that it's passed by reference. So after I call this thing, the argument B is going to be set to whatever that bit value was. And then the Boolean value is supposed to be false if you've reached the end of the file. Luke and I were talking about this just earlier before class. You're going to use the EOF member function. So in both ifstream and offstream, there's an EOF, actually not an offstream. But in ifstream, there's an EOF member function. And this guy will go true when you attempt to read past the end of the file. And it'll stay true forever after until you reset it. So think about, imagine in your head, right? You're reading bits from a file. So first bit, second bit, you get up to the 8th bit. You read the 8th bit. Now you're going to read the 9th bit. What has to happen before you read the 9th bit? A read, right? So you get the next byte from the file. Not a flush, but a read. Okay, you get the next byte from the file. You reset the bit position back down to 0 or 7, depending on how you're working, and you keep reading. Now, at some point, you're going to get to the last byte in the file. So you read the last byte in the file. EOF is still false. You exhaust the bits in that last byte. You go out and you read. Now you're past the last byte in the file, you try to read, EOF goes true, and what it's going to do is just leave the byte buffer alone. So that's the order of operations. So what you need to do is check, after you read the next byte buffer, you need to check EOF. If EOF is true, you didn't get a new byte. You reached the end of the file and you're done. That's the order of operations. So read the byte, check EOF.
Just to clarify, EOF's written by like a file without codes or something?
Yeah, EOF is weird. There is secretly a character in all files, the EOF character, and it doesn't show up when you list the size of the file or anything like that, but it's there. And that's what it's triggering. That's what it's seeing. So everybody on the planet has agreed that you can't actually read an end of file character, but it's there.
Wait, is that one of the 256 then?
It is actually. It's in the ASCII character set. I don't remember which one.
End of transmission there?
No. Maybe it's all the way at the bottom.
File separator?
That's possible. End of, hold on, beneath cancel there? End of meeting, I don't know.
Maybe I'm wrong. I thought it was /D or something like that. Huh. I'll look into it, and maybe I'm saying that wrong. Yeah. Anyway, the critical importance is, when does EOF go true? And it goes true on your first attempt to read past the end of the file, past the last byte. So keep that in mind as you're dealing with your get bit guy. Other questions about this? I sent an email out in response to a question from Ben, but I sent it to the whole group with some other tips in there. Hopefully that was somewhat clarifying.
I'm still confused as to what get into what the N argument is.
Okay, so going in, N is nothing. It's just a variable. And coming out, it has the value, N. And that's actually similar with get bit. Going in, B is just a place to hold the result coming out. Does that make sense to everybody? That's a pretty common thing to do with pass by reference variables. Going in, they're junk. Coming out, they have stuff in them.
So we need to declare like an N will be somewhere up in the...
Exactly, outside of these functions.
On that last one, why don't you just pass it back?
I could have done that, yeah. I think when I was doing this, I was thinking that maybe I would pass the EOF flag from get bit all the way out to get int, but I decided that it's not worth it. So.
I mean,
right? Because getInt, in a way, inside getInt, right, it's using getBit. And so at some point getBit's going to run out of bytes. And maybe it's going to set end of file, and maybe you want to pass that all the way out. If you want to change void to bool and pass it all the way out, that's fine. I just decided that it wasn't worth it. And so it's somewhat consistent. The argument list is kind of consistent between getInt and putInt, and that was probably my other motivation. But for example, this guy here, right? This getBit guy is actually returning 2 pieces of information every time you call it. It's returning the next read bit, and it's also returning whether you're end of file. And the only way that you can return 2 things from a function is to pass something through an argument, a pass by reference argument. Let's talk a little bit about how we're going to test this thing. Ideas?
That we did in class with just the bit representations and conversions.
So yeah, use the bit representations of ASCII characters. Use Vim to put characters into a text file, say test.txt or something like that. Don't put a lot in there, put a couple in there. You don't need to see thousands and thousands of characters, just a couple. ABC or something like that. Don't forget that there's a line feed in there, and I think VI by default will terminate lines. So even if you don't explicitly put a carriage return, like if you type AB and then save the file, Vim is going to put a line feed in there, a 10 character. And then the other thing is, so Vim will write a \n, which is 10, into file, no matter what. So if you type A, B, enter, and save it, you're going to have 2 enter characters in there. It's going to put a terminating line feed in there, no matter what.
If you do just ABC as opposed to like A space, B space, B space, or C,
yes.
on different lines, will it be interpreted differently?
So if you do A, enter, B, enter, C, enter?
Yeah, or if
you'll get
spaces between, or if you do no.
Okay, all of these are different things. So A, enter, B, enter, C, enter. You're going to get A is what, 97? 97, 10, 98, 10, 99, 10.
Okay.
If you do A space, B space, C space, you're going to get 97, 32, 98, 32, 99, 32, and then 10.
Okay.
I think the way that we're doing input, though, eats the white space when you try and read it into the character. If you put a space in between, you'll get the same output as if they were just right next to it.
Yeah, I was wondering about that. I was using, let me just check mine really quickly. I don't know why that died. Where's file in? Ah, that's what I did. Do that. So not only does get set its argument, but it returns a value, and then the cast will work. So do that. Luke and I were talking about this earlier. So.
will get you
the next character. It'll get the next byte no matter what.
Okay.
Yeah. Alrighty. So use Vim to put characters in test.txt. What else? You can use your program to put programs to put characters in a file. For example, give me an example. Let's say you're testing put int.
Just like spell a word or something.
Or even a letter, right? So what if I want to put a lowercase a?
97, right?
Yeah, and what's the word width, the bit width, whatever you want to call it? 8, yeah. So I should test that. But then testing 8 is a little bit specific. So maybe you want to test other stuff, like maybe you could take the byte for A and chop it into 5 bits and 3 bits, and then figure out what those integers are. What's the 5-bit integer? What's the 3-bit integer? And try writing those guys and seeing if you get an A. See what I'm saying? So test the variable. So you could take like 8 bits as 5 bits plus 3 bits. And then if you choose them carefully, see if you can put an A into the file. So that's putting, what else should I test?
Getting an arbitrary number of bits from the file.
Yeah. What's a way to do that?
Just load up the file that you put out, print it to the screen.
Yeah, I guess, how do you convince yourself that what you're getting is valid information?
Well, I mean, you could cast it back to characters and then see it out.
Yeah. So I'm interested in whether my variable width reads work. What's a test?
Can't you just do like grab an entire character as opposed to grabbing bits? And then see if...
But that's not what I want to do, right? I want to grab 3 bits, turn it into an int, and see if it's the right. See if it's the right
But
int.
if you grab the whole character, then you could get the whole number and then turn that into binary and then look at the 3 bits.
But I want to. That's not what this guy does. I want to use.
Oh yeah.
Why don't you just grab 20 bits and see if it's bigger than 256?
I want to be rock solid. I want to know. I want to devise a test so that when I read 3 bits or 5 bits or 28 bits, I get the right value. How can I build a test that will confirm that?
Put a couple characters in, write out by hand what their
Exactly.
binary representation should be, and figure it out.
Or even one character if you don't want to work that hard, right? So you could put 1 character in, and then read 3, and then check, right? But that's going to require scratch paper. Yeah, exactly. So I don't remember. Let's look at what. So here's a table. Let's put A in there. I keep picking on A. and let's read 3 bits. What integer should I get?
Right?
It kind of depends, right? Because it depends on your choice of most significant, least significant. But let's pretend that I'm reading from left to right, and I read 3 bits. I should get 3, right? And then I read 5 bits, and I should get 1. Okay, so again, you're going to have to understand how you're writing your bits and how you're reading your bits. But that's a test of the variable word length. Questions?
Why would you get 3?
Which one am I doing? A?
Yeah.
3 bits. So this is 2 squared, 2 to the first, 2 to the 0.
Oh, because okay.
Okay?
That's how.
Okay. Any other questions about this thing that you've run into so far? Okay, good. I finally get to talk about Huffman. I've been eagerly anticipating this. Okay, Huffman compression. The idea here is to re-encode bytes so that the most frequent bytes oops, too many R's. Have short codes and least frequent bytes have long codes. What do I mean by codes? Well, here's the default coding for the ASCII character set. All 0s and 1s, and I know that if I read 8 bits and I get 0011 0000, that represents the 0 character. That's the code for the 0 character. And these are all the codes for the various ASCII characters. Every one of these guys requires 8 bits to represent. We already discussed that this is not the most efficient way to represent this collection of characters. This collection of characters there are fewer than 128 of these characters. So in fact, a better encoding would only use 7 bits and would save space. Huffman compression takes this to an extreme. Instead of having a fixed width code, like the ASCII code is a fixed width code of 8 bits, Huffman is going to say, let's have a variable length word to represent each byte. Well, how do we decide who gets the short representations and who gets the long representations? The right answer is whichever byte occurs most frequently gets the short representation, and then the rarer bytes get the long representation. And there's a really cool algorithm for generating Huffman codes, but it depends on the particular file that you have. So it's not a code that works all the time like the ASCII character set or the ASCII codes. They work in all contexts. The Huffman code that you build depends on the particular file that you're using. So let's look at this really quickly here. What I'm going to do is encode the string Mississippi with a Huffman code. Yes, thank you. So the first thing I have to do is do a frequency count. Of the bytes. So each character is a byte, and there are no invisible characters here. This is just a preliminary example. So the bytes are the letters in the word Mississippi. So I start at the beginning of the file, Mississippi, and I see there's an M, and it occurs once. And then I see that there's a different byte, and it's an I, and it occurs once. And then I see yet another byte, an S, and it occurs once. Oh, and that occurs again. And now I hit an I, and that I count that. And then there's an S, and another S, and there's an I. Oh, and there's a new byte, P, and it happens once. Oh, and it happens again. And then there's an I, and I'm done. So you can probably imagine how you would do that in a program. You're going to go through a file, an input file, byte by byte, and you'll have an array that has 256 elements in it. And take the byte, convert it to an int, and increment the corresponding entry in the array. Really easy.
That array probably needs to be doubles.
We're going to do int arrays, but you do have to worry about overflows. Right, so if you have a large file and a lot of, say, byte 225, you risk, I guess, a lot. You would have to have more than 4 billion. So if you had more than 4 billion 255s in there, then you would get an overflow. Sorry, not 255, whatever I said, 225. If you have more than 4 billion 225s in there, you risk overflowing the frequency counter thing.
Which would just reset it.
Which would wrap around, and that would be a problem. So it's definitely something you have to deal with. Most modern compression algorithms, that's never going to be a problem, because what they do is they'll take a chunk of the file and they'll compress that, and then they'll move on and take the next chunk of the file and compress that and move on. So, and part of the reason they do that, but not the only reason, part of the reason they do that is to avoid overflows in the frequency count. So we've done the frequency count, and yes, you should be concerned about overflows, but we're not going to deal with overflows here. So there's one M, there are 4 I's, there are 4 S's, and there are 2 P's. Now at the moment, how many bits does this string consume?
8 times 11, 96.
8 times 11, 88?
Oh, yeah.
Yep. So at the moment, this guy is 88 bits. That's using the standard ASCII encoding. What I want to do is build a different encoding that gives the shortest codes to either I or S, and the longest code to M. Let's see how this goes. So what I'm going to do is build a list of the characters and their counts. So M, I. In fact, I'm going to sort that list. M, P, I, S, and I'll put their counts above. I'll put them below, I guess. 1, 2, 4, 4. And I'm going to put a box around them because these are actually going to be nodes in a tree. And the algorithm goes like this. Find the 2 smallest, the 2 least frequently occurring bytes. In this case, M and P, and join them in a tree. And put the sum of their frequencies in that new node. And treat that new node as just another byte. and then repeat. So now take the two least occurring nodes and join them into a new node and add their weights. And then take the two least occurring nodes and join them and add their weights. And you've got a Huffman tree. And then arbitrarily say that left is 0 and right is 1. Then the code for M is 0, 0, 0. And the code for P is 0, 0, 1. And the code for I is 0, 1. And the code for S is 1. These guys, because they're generated by a tree, it's not important that it's a Huffman tree, but because these guys are leaves of a binary tree, these codes enjoy what's called the prefix property, which the ASCII codes do not. This means that no valid code, can be extended to another valid code. This is really important because if I had two codes 10 and 101, I would have no way of knowing which of the characters I had encountered. I wouldn't know when to stop, in a sense, as I'm reading through these things. But because these things enjoy the prefix property, I can know when I've reached the end of a code. All right, let's see how this works.
What do you mean by going left is 0, right is 1?
So if I'm at a node and I want to get down to M, right?
Okay.
If I'm at the root node and I want to get to M, yes. Does everybody see that? Okay. In fact, I can even put that in there. 0, 0, 0, 1, 1, 1. Okay. Let's encode Mississippi using the new code. So we have M, I, S, S, I, S, S, I, P, P, I. Okay, so here's a word, M. Oops, sorry. Went a little too far there. Here's one. Here's one. Here, 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 here. M, I, S, S, I, S, S, I, P, P, I. Now I am trying to decompress. Here's how decompression works. Let me see if I can get this both on the same page here. I start at the beginning of the file. I have a Huffman tree. I read a 0. That tells me to go left. I read a 0, go left. I read a 0, I go left. I'm at a leaf node. Therefore, that's an M. Then I go back up to root and I read a 0 and a 1, and I'm at a leaf node, so that has to be an I. Then I read a 1 and I'm at a leaf. I read a 1, I'm at a leaf, and that's the way the algorithm goes. I just start at the root, read bits until I get to a leaf. That's the character. And I go back to the root, read bits until I get to a leaf. Yes, Jamie?
So if you ever read a 1, you've gotten to a leaf?
In this case, yeah.
Okay.
Yep.
Would that not be the case? Just if there's enough of them,
Well,
will eventually sort of...
No, this enjoys the prefix property, so you're done, right? But that's not the case here. For example, if I read a 0, 0 can be extended to a whole lot of valid codes in the ASCII character set. These guys don't enjoy the prefix property.
So when you encode a file with the Huffman encryption, you need to represent the Huffman tree in the file.
Yes, we'll talk about that. Yes.
That sounds fun.
Oh, it is fun.
And in the case of Mississippi, I'm sure you end up with a bigger file.
Yeah, the header is bigger than the compressed than the savings that you get by compression. But in larger files where nobody cares about compressing Mississippi, right? Just store it. Who cares, right? But for larger files, the tree can be represented. Any Huffman tree can be represented in 513 bytes.
Right, because it only has 256
So here 513 bytes totally swamps the compression. But in most files, 513 bytes is trivial for what you're compressing. It's completely negligible. All right, how many bits did we save here? Forgetting about the tree itself. We went from 88 down to what? So there's 1 times 3 here. There's 2 times 3. Oops, 33. There's 4 times 2, and there's 4 times 1. So that's 3 plus 6 is 9 plus 8 is 17 plus 4 is 21. Is that what everybody got? Yeah. 21 bits. That's a fair amount of compression, right? I mean, I went from 88 bits down to 21 bits. Of course, you're right. I have to have the tree, and I lose all the compression that I gained when I throw in the tree. Yes?
If you had another letter that had a frequency of 4 when you're making your Huffman tree, would you have just like slapped that onto the end, or would it have connected to S before those two?
You'll remember I said join the 2 smallest nodes. So go ahead.
So you would have joined that in S and then joined those 2 to the bigger.
Yeah, I don't remember. So you wanted to add another character of frequency what?
4.
Of 4. So let me just retrace my steps here. Yeah, so I would have joined. I still would have joined the S, and then I would have just joined. I would have just joined these 2 guys, like that.
But isn't the 4 of the character less than the 7 from NP and I?
But at this point, there are only 2 nodes left, and so I just joined them. So by definition, they're the 2 smallest.
Well, but it seems like going back a step from there, because we wouldn't have added that.
Yeah, it's
7 to get 11.
okay. Let me think about it. So
S says 4 too, right?
yeah, that's the thing. Everybody has 4.
Oh, but you added
I'm
2.
saying I don't think the last step that we have up there would happen. Right? Wouldn't S be joined to the new character before it was joined?
Yeah. Thank you. Yeah, it's hard to do this after the fact. But yes, you're absolutely right. So when I got to here, I'd have had a 7 and a 4 and a 4. The 2 4s would have joined. And then I would have joined the 8 and the 7. Yes, thank you. Okay. What's a worst case, Huffman? Equal numbers of every letter. Let's see what that looks like. So the worst case Huffman tree, let's say we have just a bunch of ones here. Oops. Grr. So we join these two guys and we get a 2. And so then we join the next two smallest guys and we get a 2. And then we join the next two smallest guys and we can just do these guys arbitrarily. And we get a 3. And we join the next two smallest guys here and here. It's not as bad as I thought. I'm sorry? Yeah. No, I was trying to. I'm wondering if I can get this tree.
Start out with power 2.
I thought that that's what I was going to get with equal frequency, but that's not what I get. Actually, that's just going to be what? 1 character, 2 characters, 3 characters, 4 characters?
Yeah, isn't it going to be Fibonacci? Like, if you start out with 1 and 1 and sum to 2.
No, it can't be Fibonacci. It's not fair.
Programming.
I don't know. Something like that.
Anyway, yeah. So this is maybe not the worst. This is the worst case H tree. It's still going to save me space though. Why?
You're only 3 bits deep there.
Yeah, but worst case, I guess, is if I have 1 of every kind of byte.
Or multiple but equal of every kind of byte. Right?
That's what I mean. So if I have the same number of every byte, 0 to 255, then you're not going to save anything over just a straight up 1 byte encoding. Okay?
Except for you have to include a tree.
Yes.
Losing space.
So we'll talk more about this next time. We'll do another example, but text files will compress well because you have that automatic 7-bit representation lurking in the background there. And binary files, for example, a.out, right? That has the possibility, if you go through a.out, there are going to be bytes of every kind in there, from 0 to 255. They're going to compress less well. And all of the compression that you're going to get out of that are going to be frequency savings, right? A particular byte occurring quite often. I want to leave you with a description of a really popular encryption algorithm in Unix is gzip. How many of you guys have heard of gzip? A couple people. Okay. Let me blow that up a little bit. And you just read through that a little bit, and you get an idea of what goes on in a compression algorithm beyond Huffman. I think it's interesting in the second paragraph it says literals or match lengths are compressed with the Huffman tree. So, you know, you have meta compression in a sense. But what I said to you before is still holds. At the base of every compression algorithm I've ever seen is a Huffman tree. All right, see you guys Friday.